This video explores the fundamental processes that make speech recognition possible. Speech recognition begins with capturing sound waves through microphones. These analog sound waves are converted into digital signals through a process called sampling. The digital audio is then broken down into small segments, typically milliseconds in length. Pre-processing includes noise reduction and normalization to enhance the quality of the input. Modern AI speech recognition systems need to handle various accents, background noises, and speaking styles, making initial processing crucial for accuracy. To summarize, the basic speech recognition pipeline starts with sound capture, followed by analog to digital conversion, segmentation, and pre-processing. Once these basic processing steps are complete, the signals are ready for more advanced analysis, like acoustic modeling. Acoustic modeling is a crucial component of speech recognition systems. Acoustic modeling teaches AI to recognize phonemes, the basic sound units of speech. For example, the word hello breaks down into the phonemes H-A-E-H-L and O-W. To recognize these sounds, the system first extracts spectral features from the audio. Sound waves are analyzed by frequency components, creating a spectrogram that shows how frequencies change over time. Modern systems use MEL frequency cepstral coefficients, or MFCCs, which represent audio in a way that mimics human hearing. Traditionally, hidden Markov models, or HMMs, were used to model how phonemes transition from one to another. Each state in the HMM represents a portion of a phoneme, with probabilities for transitioning between states. Modern acoustic models now use deep neural networks for more accurate phoneme recognition. These networks learn complex patterns from thousands of hours of labeled speech data. Acoustic models are trained on large datasets of speech with corresponding phoneme labels. The model learns by analyzing audio features and adjusting its parameters to better predict the correct phonemes. Once trained, the acoustic model can recognize phonemes in new speech by calculating probabilities for each possible sound. The system analyzes sound input and outputs probabilities for different phonemes, choosing the most likely sequence. What makes MFCCs so effective is how they mimic human hearing, focusing on the frequency ranges we're most sensitive to. The MEL scale is logarithmic, giving more importance to lower frequencies, just like our ears do. Acoustic modeling creates the foundation for speech recognition by translating sound waves into probable phonemes, which can then be processed by language models. Language modeling is a critical component in the speech recognition pipeline. After the acoustic model identifies potential phonemes, the language model determines which words these phonemes likely form. Language models help AI understand the context and probability of word sequences. For example, in English, weather is more likely to follow the than eat. The model assigns higher probabilities to more natural phrases. Language models calculate probabilities based on grammar rules and statistical patterns learned from vast text corpora. By analyzing millions of text examples, the model learns which word sequences are common and grammatically correct. Modern language models use neural networks to capture patterns in language. Recurrent neural networks, or RNNs, maintain a memory of previous words through feedback connections. Transformer models use attention mechanisms to capture long-range dependencies between words, significantly improving recognition accuracy. Language models excel at resolving ambiguity in speech by considering conversational context. When speech contains sounds that could be interpreted as different words, the language model uses context to determine the most likely option. In this example, the model recognizes that flight information is much more likely in an airport context than slight information or right information. To summarize, language models are essential for speech recognition because language modeling provides the contextual understanding that makes modern speech recognition systems truly effective. Before deep learning, speech recognition systems used separate components for different speech processing tasks. Deep learning revolutionized speech recognition by enabling end-to-end learning, where a single neural network can process raw audio and output text directly. This integrated approach eliminated the need for separate feature engineering and modeling components, leading to much better performance. Three main types of neural network architectures have been crucial for speech recognition. Convolutional neural networks, or CNNs, extract spatial features from audio spectrograms, similar to how they process images. Recurrent neural networks, or RNNs, process speech data sequentially, capturing temporal patterns in the audio. Transformer models use attention mechanisms to process all parts of a speech signal simultaneously, allowing them to capture long-range dependencies more effectively. The impact of deep learning on speech recognition has been dramatic, with word error rates dropping from over 20% to under 5% in many applications. Traditional systems in 2010 had error rates around 20%. The introduction of deep neural networks in 2012 began the revolution, with CNNs and RNNs reducing errors to 8% by 2015. Transformer models further reduced error rates to around 5% by 2019, and current systems achieve less than 4% error in many scenarios. Transfer learning has made speech recognition more accessible across languages and domains. A model pre-trained on thousands of hours of English speech can be adapted to Spanish with much less data. This approach provides several benefits. It requires less training data, enables faster adaptation to new domains, works across multiple languages, and makes speech recognition possible for low-resource languages. Modern AI speech systems operate in real time through efficient algorithms and specialized hardware acceleration. Speech is processed in small chunks as you speak, allowing for immediate responses without waiting for you to finish speaking. One crucial technique used in real-time speech recognition is beam search, which explores multiple interpretation possibilities simultaneously. Instead of committing to a single interpretation, the system maintains a list of the most probable paths, ensuring accuracy even when words sound similar or speech is unclear. Personalization is another key feature of modern speech recognition systems. They adapt to individual users' voices, vocabulary, and speech patterns over time. As you interact with the system, it learns your unique speech characteristics, improving recognition accuracy dramatically. This personalization is achieved through continuous learning algorithms that fine-tune models based on your interactions. The system constantly updates itself through a feedback loop, collecting your speech, producing recognition results, receiving feedback, and improving the model accordingly. Contextual awareness is another powerful feature of modern speech recognition. The system adjusts recognition based on device location, active applications, or previous conversations. For example, the phrase, "I need to get a note," would be interpreted differently depending on whether you're using a music app, a note-taking app, or a banking app. Let's summarize the key advances that enable real-time speech recognition systems to work so seamlessly. These technological advances combine to enable the seamless voice assistance and transcription services we use daily, making human-computer interaction more natural and efficient.